Do you want to architect for independent systems that you can evolve, scale, and operate individually? And do you want to make sure you set up resiliency within the communications among those systems? Then I have some content for you. Hi, I'm Dirk from the AWS Solutions Architecture team in Germany. And today I want to introduce you to some fundamental integration patterns in the microservices scenario. In my experience as architect, two principles are really important when it comes to designing systems. One is divide and conquer, the other one is loose coupling. When you deal with microservices, you already apply divide and conquer. And a good way to reach loose coupling is asynchronous messaging. Now, when we talk with our customers about the design of the communications landscape for their microservices, we often hear that customers have REST APIs on their radar, but not necessarily asynchronous messaging. And we think that asynchronous messaging can have a number of advantages in certain scenarios. And of course, as always, that's not the solution to every problem, right? For every scenario and every architecture, you should make sure that you use the right tool and technology. And when it comes to integration, messaging is a solution in many cases, but in other cases, HTTP-based APIs or streaming are better solutions. Now, the patterns I have talked about already that I brought for you today, they are of course of general use. So they are not restricted to the microservices context. You can apply them for all your integration scenarios. But for the reason I've mentioned before, today I want to discuss them in the context of microservices. And since the patterns are of universal use, this talk could also be named Application Integration Patterns not only for microservices. Let's have a look at the agenda. So I will have 1-2 more sentences of motivation why we are talking about this in the first place. And then I'm going to introduce you in some of those fundamental integration patterns, all based on asynchronous messaging. But to make this more tangible and put more flesh to the bone, I also brought some real-world use cases that I want to discuss with you and that apply those patterns. And of course, in the end, I cannot let you go without a few resources and a call to action. Okay, a few more words on motivation. And I would actually like to start this with a quotation from a former colleague of ours, Tim Bray. What he said is, if your application is cloud native, large scale, or distributed, and doesn't include a messaging component, that's probably a bug. And Tim is absolutely right, I think. So what's the inherent characteristic of synchronous systems? They are loosely coupled, at least during runtime. If you think about your landscape of microservices and a request comes in from outside, that request probably requires to wander through a number of other services to get fully processed. And if you have synchronous communication, on each step in this path, you block some resources there because every part is waiting for the subsequent ones to get done. And with that, you can easily imagine that if you have a problem in some of those downstream systems, that can easily accumulate in upstream systems and put your entire system at jeopardy, particularly if upstream systems try retrying their requests. And that is the reason why we have mitigation patterns like circuit breaker in the first place. And other than that, of course, some things simply take too much time to wait. We also have one example in the use cases I brought, or are asynchronous by nature. But now let's have a look at the patterns I brought today. And if you are an architect or a software developer, you are probably used to talk about patterns. Patterns are a great means for architects and technologists in general to talk about stuff because they are a lingua franca, so everybody understands what the other person means. If you look at software development, for instance, there's the Gang of Four pattern catalog, which is probably known to you. And when it comes to integration patterns, there's also a catalog that I would consider a standard catalog, which is called Enterprise Integration Patterns. which was authored by Gregor Hope and Bobby Wolf. And you can also access and read about those patterns online on Gregor's website. I'll pause a moment here so that you can take a picture of the QR code and visit the website. Okay, now let's start with the very beginning, message exchange. And this addresses the question, how can we send messages from one end to the other and what is the reaction? And the first one is one-way messaging. And it's quite simple. What it basically means is we have a sender and we have a receiver. And the sender sends a message into a message channel, and from there, receiver receives it. And that immediately shows you that this message channel decouples sender and receiver from each other. So with this additional component, both ends don't need to know about each other. The expectation, of course, here is that there is no response from the receiver, just the message should be sent through and reach the receiver eventually. And we can further distinguish now into different message intents. This relates to the purpose of the message that we want sent. So one example would be a command message. In this case, the sender wants to instruct the receiver to do something. Or a document message. In this case, the sender wants to transfer data to the receiver. And there's also event messages where the sender just wants to notify the receiver about something, and then the receiver has to know on its own what to do with it. In contrast to that, we have the request-response pattern. And here we have not only one message channel, but we have two, because one is for the request and one is for the response. And to be more precise, we call this an asynchronous request-response pattern. So the requester sends a request message, message A, into a channel. The responder receives it, works on it, and the response is sent back to the other message channel as message B to the requester. Now a response is expected, obviously. Now this might immediately raise two questions. Now, how can the responder know where to send the response? And the other question is, how can the requester know how to assign an incoming response to a previous request? So those questions are addressed by the return address and the correlation ID pattern. The return address pattern is a piece of meta information that the requester injects into the request message. The responder can extract it from there and use this information to identify the message channel for the response. The correlation ID pattern means that, again, the requester inserts some meta information into the request message, and this is a unique identifier for this request. Now the responder is asked to forward this correlation ID into the response message, and then the requester can assign the response to the previous request. And we can further categorize the left and the right-hand side. What we see on the left-hand side is actually an integration pattern. So we integrate the left and the right-hand side and use the message channel for it. On the right-hand side, we have an actual conversation between the requester and the responder, and it's a composite pattern. And we also call this a conversation pattern. Now, we have been talking about message channels already, but in a rather abstract manner. And there are different kinds of message channels, and we want to understand what those are. The first one are point-to-point channels, and they are implemented by queues. What we can see in the diagram here, there's a sender that sends messages into a queue, and we have one or more receivers on the right-hand side. We could also have multiple senders, but just to keep the diagram simple, I only put one here, but there can be multiple ones. Now the semantics is that each message from the queue is delivered to one consumer. Now if we look into the potential situation that the queue has a lot of messages which overwhelms the existing consumers, we can simply add more consumers to it, and each additional consumer can also add to consuming those messages. So it's very easy to scale out on the consumer side. And because of this behavior, a message queue can also be considered a load balancer. And there's an additional very useful characteristic of message queues, which is that message queues usually can buffer messages. And with that they can flatten peak loads for you. So maybe you cannot scale out anymore on the receiver side, or maybe you don't want to scale out anymore to cap the cost on the consumer side. Then the queue can keep the messages for you, and all your receivers can consume those messages in their individual pace. The other fundamental message channel are publish-subscribe channels, also known as topics, and their behavior is also called fan-out. So what it means is we have a publisher now. That's what the sender is now called, because we have the publish-subscribe scenario. The sender is called publisher. The receivers are called subscribers. The publisher sends messages into the topic, and each subscriber receives every message. You can compare it with switching your radio on. That means if you switch your radio on, you will listen to it, and the same applies to your neighbor and so on. But also, if you switch your radio off, you will stop listening. And if you switch it back on 1 hour later, you can continue listening, but you will have missed what was taking place in between. And the same applies also if you turn down your subscriber processes or they run into a failure. Apparently, the concrete products in the market have various mechanisms for retrying to deliver those messages, but in general, there's conceptually no buffering with those topic messages here. But now there's another question that probably comes up already for you. When every subscriber receives every message, what if the pure amount of messages in the topic is so much that it overwhelms the subscriber processes? You cannot simply add another process to share the load, because each additional process would also receive every message. So we need to think about something else. I want to park that question for a minute. I will come back to it with a solution, of course. But now I would also like to share what concrete AWS services are there that implement those messaging channels. And let's first have a look at the cloud native and serverless services, which are also the focus for my sample use cases I brought later. So I will make use of them there too. For the queues, we have Amazon Simple Queue Service, and for topics, we have Amazon Simple Notification Service. But just for the sake of completeness, you might also be constrained to industry standard protocols like JMS or AMQP. In this case, there's Amazon MQ, which manages a RabbitMQ or Apache ActiveMQ broker on your behalf. And it's often used for workloads that currently reside on-prem when they are shifted to the cloud. And also for the sake of completeness, I also wanted to mention the AWS IoT Core message broker, which offers MQTT over WebSockets, and HTTPS for publishing for apps in the IoT context. But we're not going to look into it any further today in this talk. You might ask yourself, what about streams? Streams might sound or appear a little bit similar to topic messages. And in fact, they are. Both messaging topics and streams are fan-out patterns. But what's the difference? So message processing is actually meant to work on each individual message as a unit of work. So that means every message that comes in, and remember the message intent patterns that I have mentioned before. We have command messages or document messages or event messages. Each single message has a value here. And when we look at the consumption model, each message that is consumed is then also gone. It disappears with the consumption. And to visualize it a little bit, here the picture on the left-hand side could represent a message, and this is a unit of work. If we look at stream processing, we have the same picture again, but we now divided it into numerous tiles. And you can imagine that every tile in this picture is a stream message. And you are usually interested in batches of messages, and that is the unit of work when you go into stream processing. You usually don't look at one message in separation, but you look at batches of messages to identify trends, to calculate aggregates, and so on, but maybe also to find outliers or so. And then again, you might be interested in one concrete message, but still you have inspected a large number of messages to get to that conclusion. Another difference is the consumption model. When you consume messages from a stream, they remain in the stream and you can consume them later. You can also say you can replay the stream later until an expiration timeout fires, and then the messages will disappear. That depends on the concrete products that you use. And you might also ask yourself, what about buses? Or to be more precise, event buses. Event buses also implement the fan-out pattern, and they are maybe similar to message topics, but they are more purpose-built services. So usually they come with integrations to commercial software, they come with advanced message routing options, they are also opinionated in terms of how the payload should look like. So they come with a lot of functionality that pure topic messaging doesn't have. In the sense of this talk today, there's no really a conceptual difference though between sending messages through event buses or topics, and that's why I treat them equal, and that's why I also focus for the rest of this talk simply on queues and topics. Just to still summarize all the other AWS services that are in place for fan-out pattern, we have for streaming the cloud-native and serverless Amazon Kinesis family with Kinesis data streams, Kinesis data firehose to offload large batches of events into a sink, for instance, Amazon S3. And we have Amazon Kinesis data analytics to run analytics on sliding windows of streams, for instance. And again here, as with messaging, if you are constrained to open source software like Apache Kafka, there's also Amazon Managed Streaming for Apache Kafka that manages a Kafka cluster on your behalf. And since we also mentioned buses, there's Amazon Event Bridge as a cloud-native and serverless event bus service. And as I said again, for the sake of this talk, I don't distinguish between event bus and message topics. I purely focus on the concept of fan-out messaging, and therefore we have queues and topics for the remainder of this talk. Okay, now let's have a look at another pattern, which is the topic queue chaining pattern. And here we want to revisit the question from before: how to scale consumers for published subscribe channels. And this is actually the solution for it. So let's look at it. We again have the producer. The producer sends messages into a topic. And now we can apply a composite pattern, which is the topic queue chaining pattern. What we do here is that we do not directly attach our subscribers to the topic, but we put a queue in between. And that means now that we can actually also scale out on the consumer side because we have the queue in between. Which brings us to the best of both worlds. We have fan-out functionality from left to right, but we also have consumer scale-out functionality on the right-hand side, and we can make use of the buffering load balancing functionality of queues, all at the same time. Another pattern that I wanted to introduce today, because it's quite helpful, particularly when something goes wrong in production, which is the dead letter queue pattern. So imagine a producer sends messages into a queue. They get consumed by consumers. And now it happens that message C runs into an exception, and it runs into it repeatedly. Now, you don't want to continue with that forever, right? Message C is delivered to a consumer, runs into exception, goes back into the queue, and again and again. So what you can rather do is that you want to take this message offline, because such a message can either be a sign that there is a transient failure, or maybe it is a poison pill. Poison pill doesn't necessarily mean there's something malicious going on. It just means it's a message that will always run into an exception when it's being processed, maybe because the consumer code is based on wrong assumptions or so. So for that, you can set up a dead letter queue and can instruct your queue, hey, after so and so many times that my message ran into an exception, please take it out and put it into the dead letter queue. And there, application operations can inspect it safely. You don't need the open heart surgery anymore, and you can investigate why this message always fails without the hassle of production. I also wanted to clarify a few technical terms that usually come up in the context of messaging. Not with every product, but those 3 terms that we have here, for instance, come up in the context of Amazon SQS. So visibility timeout, in-flight messages, and message acknowledgement. And let's have a look at the first case where we have a fast enough consumer, and you will quickly see what this actually means. So let's imagine we have the blue queue here, and we see the state of the queue from left to right over time. Now, in the beginning, we have a producer that sends a message into the queue. It's message A. And that message is now in status stored. After a while, there's a consumer that connects to the queue and wants to consume a message, and it receives message A. From that moment on, the status of the message is in flight. And this means it has been delivered to a consumer and it is being processed there. But the consumer has not finally said, okay, I'm good with working on that message and it can be deleted now. And what also happens at the same time is that the so-called visibility timeout starts. And it means, as the term already suggests, message A is invisible to other consumers during that visibility timeout. So consumer 2 in this example asks the queue, hey, give me a message, and it will not see message A. Eventually, consumer 1 is done with working on the message, and it can now acknowledge the message. And acknowledgement means the messaging system is notified, okay, consumer is done, and the message will be deleted now. And actually, that's also the concrete operation for Amazon SQS, delete message. Okay, and from that moment on, the message is in status deleted and will remain in that message for the rest of all time. Let's have a look now at another case where we have a not fast enough consumer. And you can maybe already imagine what this should mean. So again, we have producer 1 that produces a message, sends it into the queue, it's in status stored. Consumer 1 goes to the message, asks it for a message, so from that moment on, the status is in flight and the visibility timeout starts. Also, when consumer 2 tries to receive a message from the queue, it will not see message A. And as we can see here, we have reached the visibility timeout end already, and consumer 1 is still not done with working on the message. And from that moment on, the message is back in status stored, and it is visible for other consumers again. Okay, so consumer 2 can now consume or receive the message and work on it. And again, from that moment on, message status is again in flight, and the visibility timeout starts. And hopefully consumer 2 has more luck now with working on the message and can acknowledge it early enough. Of course, the visibility timeout is something that you can configure on Amazon SQS, for instance. But you also should be aware that there is something like that visibility timeout, and you should configure it in a way that matches the behavior of your consumers. Another important pattern is FIFO queues, and that's a requirement that comes up every now and then, or maybe even more often than every now and then, that the requirement says, I want strict order in the delivery of my messages. And FIFO stands for first in, first out. So we want strict order for message delivery. As we can see in this diagram here, messages come out in the same order, guaranteed in the same order as they have been sent to the queue. And you can maybe imagine that this also comes with a price. Because if you think about a web scale messaging system, you will have a hard time guaranteeing this. So every time you want really strict order, you kind of need to reduce the concurrency or the scope a little bit. And that has nothing to do with quality of code, but that's pure physics. And now we have looked at one consumer only. What if we look at a number of consumers? So that implies that we have concurrent messaging concurrent message consumption. In this example, we have 3 consumers. Now, if the producer sends the messages A, B, C, D into the queue, into the FIFO queue, they are, for instance, delivered to consumer 1, 2, 3 in the strict order. Those consumers work on it. But now it happens that the second consumer is already done with working on message B before the first consumer is done with working on message A. Can happen. So in our protocol log, message B appears as the first one. From that moment on, the second consumer is available again and can receive the next message, which is message D, and it can now work on it. Then in our example, message A is done with processing, so it appears as the second item in our log. Then it happens that the second consumer is already done with message D before the third consumer is done with message C. So that brings us to the conclusion that the actual message processing time within your consumer code can vary, and that can also lead to order validation in our consumer processes. Right? It has nothing to do with a messaging system. But there are patterns that can also address this, and with the help of those patterns, we can make sure that the messaging system takes care of this strict order. And one pattern that helps here are message groups, which are discriminator attributes that you can add to your messages as meta information, for instance. And I want to take the example of Amazon SQS message group IDs. So let's have a look again at the previous example. Now we have again messages A, B, C, D, but they appear in different colors, and the different colors represent different message groups. So we have the blue message group, we have the green message group, and we have the red message group. And every message group gets their own message ID in the meta information of each message that is a member of this group. Let's see what happens here. So message A is being sent to the first consumer. It can start working on it. Message B is sent to the second consumer, which also starts working on it. Now again, we have the case that the second consumer is quite fast, or the message as such didn't take so much time to process. It appears as the first one in our log. And now what happens? The second consumer is receiving message D as next message and not message C, although message C would have been the next one in the order. What happens here is that we still have a message from the blue message group in flight. And the behavior of the SQS FIFO queue with the use of message groups is, as long as there is a message of a given message group in flight, no other message of this group will be delivered to another consumer. Right? And that's why we have message D now appearing in the second consumer. Message A is done with consumption, it appears in our log. Then message C is left and can also be sent to the first consumer. Second one is done with message D, and the first one is also eventually done with message C. So this brings us to the following conclusion. We did not manage to retain the global message order in our log, but we retained the local message order. That means the order within each message group. And this allows us now to scale out again on the consumer side regarding the number of message group IDs that we have. And I already mentioned it, we have now applied a local message order, which refers to message groups. So we can distinguish between local message order and global message order. What if we actually need global message order? Well, for that, we can use one message group for all messages. But this has the respective implications that, of course, it will lead to a sequential processing of those messages. And also interesting to mention, there are not only FIFO queues, but there are also FIFO topics. The good news here is we inherently don't have current consumers, so we don't need to take care about that. But actually, what happens when we want to apply topic queue chaining? Yeah, do you remember the pattern, the composite pattern that we can apply to make sure that we still can scale out on the consumer side if we want to use the fan-out functionality? Well, the good news is here, Amazon SNS FIFO topics also support the message group pattern. And when you connect an SNS FIFO topic with an SQS FIFO queue, those message group IDs are also forwarded into the respective queues. Okay, and I still have a few message routing patterns that I also wanted to share with you. The first one is the message filter, and it targets the requirement that you maybe only want to receive a relevant subset of messages from a topic. We have learned that for topics, every subscriber receives every message, but maybe you are only interested in 95% of those messages. In this example, we have two subscribers here, the top one and the bottom one, who are only interested in the green or the red messages respectively. And for that, we can apply the message filter pattern. So those subscribers can instruct the topic, please apply the filter color equals green or color equals red, and only the ones that pass that filter, that's the ones I'm interested in. So this is controlled by the subscriber completely, and as always, the publisher remains totally unaware of it, which it usually does anyway. I'm mentioning this particularly also because there are ways to implement the same functionality without messaging, and it comes with a lot more effort. The recipient list pattern is a pattern that you could use to apply the same functionality. Now we have the requirement to send only relevant subsets of messages to each subscriber. If we have a publisher here, there has to be something like a recipient list component, which can be a standalone component or it can be embedded into the publisher that knows who is the relevant recipient for every message. So that means it probably requires additional code that you need to maintain and operate. It requires configuration, and it potentially adds coupling between both ends. And that's something that we want to avoid, of course, if possible. And if you use topic messaging, all this functionality comes implicit. Another message routing pattern that I wanted to share is the scatter-gather pattern. And this addresses the question how to distribute a request to relevant or interested parties and capture their individual response. And the context for that is that we have election or parallel processing, and we want to search for the best response, or we want to accumulate responses and so on. And again, we have a requester here. It can send out the messages into a topic. In a different context, we have different services that implement those responders. They can work on the request and send back the response into the response queue, which brings us back to the context of the requester service. And those responses can there be aggregated and processed for the final response. So you can probably remember that we introduced the correlation ID and the return address patterns in the beginning. Of course, we would need those patterns here too, because we have again a conversation pattern. So this entire architecture here is a conversation pattern because the requester communicates with the responders and back. And the responders need to know where to send the response to. and the requester process also needs to assign those responses to previous requests. And the nice thing is that only with the term scatter-gather, you can make clear that this architecture here is meant, and everybody who knows that pattern immediately understands what you mean. Okay, now, as promised in the beginning, I brought also a number of use cases to put more flesh to the bone and make this more tangible. And the context for these use cases is wild rides. Wild Rides is our favorite technology startup, and it disrupts passenger transportation, individual passenger transportation, by replacing traditional taxi cabs with unicorns, because unicorns are much more fun and, of course, more magical than old guard taxi cabs. So Wild Rides has a nice microservices-based backend. They run all serverless services on AWS, and they are technology-wise quite advanced. And they were friendly enough to share some of their use cases with us today. Let's have a look at the first use case, submit a ride completion. So what's going on here? Imagine there's a unicorn, and the unicorn has just dropped off a passenger to their final destination. And now the unicorn wants to notify the Wild Rides backend about it to make sure also that it eventually gets the fare for it, that the Wild Rides backend would then also collect from the customer. So it uses the Wild Rides Unicorn app and the app sends a request to the backend, and there's the ride management service which resides on AWS. It gets that post request with all the ride details that are required there and what happens in here. So first thing is you probably want to have a managed API gateway component, and we have this here as Amazon API Gateway, so that you don't need to deal with this on your own. And then next we have a completed rides processor. That's a piece of code that then actually processes on the information that is being submitted by the client. It probably wants to store it in a database, and then responds back to the client, 201 created, hey, there's a new resource for you, and provide also the representation of the new resource. So far, so good. But the ride management service doesn't live in isolation within the Wild Rides backend. There are a number of other services who are interested in this information too. For instance, there is the customer notification service, there's the customer accounting service to finally collect also the fare. There's the customer loyalty service. Of course, there has to be data lake ingestion service. And there's the extraordinary rides service. And this is a special one which is only interested in rides that have fare and distance across above certain threshold values. Now, the big question is, how can we integrate this? Integration via database, maybe. I mean, there's already a database in the first service that receives the request, and we could simply have all those other services connect to that database. No, we don't want to do this. I mean, this really adds so much coupling to the architecture. This is a case which I usually want to call lousy coupling, because it makes it so inflexible. If you change then the database schema of the incoming service, then you will probably delete all the integration with the other services and everything will break. Or to put it in words of Roy Fielding, what he says to a similar situation, there's so much coupling in the architecture, it should be X-rated. So we don't want to do this. That's why we have the red traffic light here, but also I have put it or I used a photo where the shape is a heart, because if you talk with your architects at home in your company, you should be friendly to them and explain it nicely. Okay, so next option, integration via REST APIs. We just mentioned Roy Fielding, and of course REST APIs are a perfect means to reach also loose coupling. I mean, it's based on the web architecture and it's apparently a loosely coupled system, a very large one. Yes, we can absolutely use REST APIs here too, but it comes with an effort. So we would be back to the recipient list pattern. So we would have additional code or even a separate component that knows where to send those HTTPS requests to, right? And we don't want to manage that additional component and codes that is also needed for this component. And also, we would have to have a self-managed filtering, right? The filter for the extraordinary write service, we would have to implement it on our own. Okay, now next question, integration via messaging. Well, absolutely. I hope you already thought absolutely before or without the fact that it already is stated on the slide here. But yes, it makes it really simple. So we could simply add the write completion topic here, an SNS topic in this case, and all the interested services on the right-hand side can subscribe to it on their own behalf, and the write management service doesn't need to know anything about it. Also, we can use the SNS message filter functionality so that the extraordinary write service can handle all that message filtering on its own. And if you want to also add resilience regarding the fact that we sometimes have to take our services offline for maintenance, or maybe there are bugs, then we can also apply the topic queue chaining pattern and make sure that we don't lose any messages if we are offline with our consumer services on the right-hand side. All right, that was the first use case. Let's have a look at the second one, pre-booking campaigns. So WildWrites now runs massive campaigns through all kinds of media with the current call to action, book this week. So what it means is book your write for next week, already this week. And in the first architecture approach that we take here is that we have it all at once, and you will directly see what I mean with that. So we have the WildWrites customer. The customer uses the WildWrites app and sends a request for a pre-booking to the backend, and it lands in the write booking service. Again, we have managed API gateway and then the pre-booking processing resource that takes care of it. It will probably store it in the database and respond to the client with 201 created. Hey, all good. We have your pre-booking and it's scheduled and so on. Now, WildWrites decided to run instead a massive campaign with the CTA book today. Book the writes for next week already today. So now we expect a lot more traffic that hits us here. And we now want to apply some internal decoupling even within one service, also through messaging. So again, the customer uses the app to submit the pre-booking. It lands again in the write booking service. What's different here is now we have a pre-booking pre-processing resource. And this one does a sanity check if certain criteria are met, but not more. And then the pre-booking request is forwarded into the pre-booking forwarding topic. And only then the client can, the backend responds to the client, this time 202 accepted, because we now have a process that takes a bit more time. I mentioned this in the beginning. Sometimes processes take a bit more time. So we can make use of the HTTP idea for this. We respond with 202 accepted and return a representation of a task and a link to a status update that the client then can use later. Under the hood, what happens there? We have the rest of the write booking service, and it can now, and hopefully through the means of a queue, so that we can make sure no pre-booking request is missed, do the actual processing of the pre-booking. Yeah, so the important piece here is from a user experience, you want to make sure that no pre-booking request is missed. So we want to make sure that we accept it and answer quickly to the client, but the actual processing can also take place a few seconds later. And just to make it a bit more nice here, I also put a second example for a service that is also interested in this notification here, which is the data lake ingestion service. And of course, before the question comes up, there was no space left for the database icon on the bottom right in the write booking service, but of course the pre-booking processing resource would actually, of course, persist the pre-booking request. Okay, now let's look at even more internal decoupling, because there is now another CTA that comes up in a campaign which says book your request, your ride for next week already now. So imagine it's at prime time in a TV show or so, and we expect a lot of traffic from 1 second to the other. What we can do here with even more internal decoupling is to put an SQS queue in front of the pre-booking, pre-processing resource. With that, we don't have to worry about the preparation of any resources to take care of the load, as SQS will handle it. On the other hand, we would have to expose the SQS API to our client. So we can do this if we implement the app on our own. But if you want to open your API also to third-party developers, for instance, you would not want to do this, of course. Then again, you could put the managed API gateway in front of it, and you come back to the same API look and feel that you had before. All right, and now also let's have a look at the data lake ingestion service, and I want to use it as an example where streaming is actually a better choice than messaging. Because unless you really want to do something fancy, you don't have to have that data lake ingestion service, but you could really directly connect the data lake ingestion stream to the pre-booking forwarding topic and have it offload all that data in the raw data tier of your data lake within the scope of your modern data platform. All right, last use case for today, instant write RFQ. So, do you remember the scatter-gather pattern? It was a means to run distributed requests with parties that are potentially interested to respond, and how to collect those responses and how to process it. Since WildWrites is really a progressive company, it has thought about a use case that the customers don't want to just book the next available unicorn around the corner, but they want to run an RFQ, a request for quotes, with all the unicorns that are in vicinity of the customer. Okay, so how does this look like? We can use the scatter-gather pattern now to implement this. Again, WildWrites customer uses the app, sends a request to the ride booking service that it submits now the RFQ. Again, API gateway that receives the request, and it lands in the RFQ intake processor. There we would probably store it in a database to have it persisted, and then forward it into the RFQ share topic. And this is the topic from the scatter-gather pattern that is used to distribute the request to all interested parties. Only then we can send a response to the client to accept it. Hey, we have received your RFQ request. We're working on it now. Let's assume there's a default timeout of 5 minutes. Now all unicorns who are interested have 5 minutes to work on it. Now we are going to leave the scope of the ride booking service and come to the unicorn management service. And there, let's assume we have unicorn management resources, UMRs, that represent the unicorns that are in vicinity to the customer and who receives that message now from the RFQ share topic. And let's further assume those UMRs have the means of sending push notifications to the unicorn apps, and the unicorns get notified, can submit their quote, and their quote can be good in the from the viewpoint of the customer in terms of good price, but maybe also nice goodies like free drinks during the ride. That's for the customer to decide. Now, they can use, the UMRs can use, again, the response address pattern, and of course also the correlation ID patterns here to send back their responses into the RFQ response queue. We have an aggregator resource here that consumes all those messages, does a pre-aggregation, and stores it again into the database. What can the client do? So while the request is running, they can retrieve a status update. Okay, because we have seen before in the response, there's a link to refresh the status. We can see it here highlighted in the response. Now, client sends a request to refresh the current status. It lands in API Gateway. It then lands in the RFQ result processor. And the processor can check in the database, what's the current status of the RFQ? It's still running. Okay, so we see it in the response, status running. And again, we see a link to to refresh the status. What else can the client do? Well, it can retrieve another status update. Same procedure as before. And what we see now in the result, status is done. And now we find a link to the result in the representation that comes back. Now, what can the client do last? It can retrieve the RFQ result. So use the link from the previous response and retrieve the result. And then the customer can make up their mind which one of those quotes is the best fitting one for them. And of course, you could also use a means of push notification to notify the customer app that the RFQ is done. Okay, that were the use cases I wanted to share with you today. I don't want to let you go without some resources and a call to action. So first of all, if you want to read about all those use cases and patterns from this talk again, and maybe a few more, you can visit the blog series that are linked here. And if you want to gain hands-on experience with building the use cases from this talk and a few more, there's also a hands-on workshop, which is called Asynchronous Messaging Workshop or Decoupled Microservices Workshop. Of course, you can also reach out to your friendly AWS Solutions Architect if you need to have some support for your integration questions. And one thing to keep in mind, of course, always, that's the one takeaway you should have for today, loose coupling is always better than lousy coupling. And with that, I want to thank you for joining today. It was a pleasure talking to you. You can see my contact details here. Please feel free to reach out to me on LinkedIn or on Twitter. I'd like to discuss your integration scenarios with you if you're up to it, so just do it. I'm always here to help. Thanks a lot and have a great day. Bye-bye.